Welcome to Lecture 6.4, the Rayleigh quotient. A few lectures ago, we derived the spectral resolution of self-adjoint maps using the spectral theory of linear maps. Let me give a quick recap as to what that was about. So H is a linear map from X to itself. Then X breaks up as a direct sum of eigenspaces, E lambda 1 up to E lambda k, where these are distinct eigenvalues. Now I should say generalized eigenspaces. However, if H is self-adjoint, then these are genuine eigenspaces, and moreover, the eigenvalues are real. Now the identity map is just the projection, the sum of the projections onto each of these. So I call that P, let's say P lambda 1 or P1. I don't know if you need to put the lambda in there, up to P lambda k. I think in my lecture I did not put a lambda subscript, but this is fine. And then H is just a linear combination of these things. So H projects it onto the first coordinate and then multiplies it by lambda 1. And then projects it onto the, I don't want to say coordinate, I should say the kth eigenspace, and then scales it by lambda k. So the go-to example that I'm going to keep coming back to that I like is, so here's H equals 3002. So this maps this unit square. It stretches it out. It stretches the x value out by 3 and the y value out by 2. So it maps this unit square to a rectangle of side length 3 and 2. And I've said that self-adjoint maps you can always think about like this. They all look like this if you use a basis of eigenvectors. So I like to say if you tilt your head the right way. So if your eigenvectors are going to be something like this, then there's going to be a self-adjoint map that sends this unit square, or that just stretches out each side and sends squares to rectangles. Okay, so all of this used the spectral theory of linear maps, especially right here. And this was this is a fundamental result, but it depended. One thing we used was the fundamental theorem of algebra, that every polynomial over the complex numbers has a root. In this lecture, I'm going to give an alternative proof of the spectral resolution of self-adjoint maps. And this will have several advantages. For one, it does not assume the fundamental theorem of algebra. Two, if we are over the real numbers, in other words, if our entries in H are all real, then we completely avoid the complex numbers. And finally, it leads to a so-called min-max principle, which characterizes eigenvalues and eigenvectors as critical points of a particular function. And this function is relevant in a number of numerical algorithms. Throughout this lecture, we will assume that H is a self-adjoint linear map with eigenvalues lambda 1 up to lambda n in non-decreasing order and corresponding orthonormal eigenvectors v1 up to vn. Let's do a quick recap and warm-up that with respect to this orthonormal basis, if we have a vector x, let's say a1 v1 plus up to an vn, then the inner product of x with itself is just the inner product of aj vj with some aj vj. You get n squared terms here. Most of them are 0 due to the fact that they're orthogonal. And we just get a1 squared plus an squared. So the inner product of x with hx is going to be similar. With respect to this eigenvector basis, this is diagonal. So in other words, a1 up to an Now h is going to be lambda 1 to lambda n, and a1 up to an. This is just going to be lambda 1, a1 squared, plus lambda n, an squared. So think of this as like a linear combination of the sum, or of the squares of the coefficients of x. So I'm saying this because we're going to be using these things, especially this one, throughout this lecture. It's time for a definition. Given a self-adjoint linear map H, its Rayleigh quotient, which we denote as r sub h of x, or just r of x if h is understood, it's a function defined for all non-zero vectors that outputs a scalar, and it's defined as the inner product of x and hx divided by the inner product of x with itself. Now here's how I like to think about this. 1 over the inner product of x with itself is just 1 over the norm of x squared. And this is 1 over the norm of x times 1 over the norm of x. So we have an x appearing twice in the top of this fraction, and we could distribute or attach on each one of these 1 over norm x to each one. In other words, this thing here we can write as the inner product. We can take the normalized version of x, make it a unit vector, and that is x divided by norm x, and just take the inner product of that unit vector. Let me call this u with hu. And that's the Rayleigh quotient. So let's spend a few minutes trying to understand geometrically what this really means. First of all, it's easy to see from this here that the Rayleigh quotient is not affected by multiplying x by a scalar. In other words, the Rayleigh quotient of kx is equal to the Rayleigh quotient of x, and all of this is equal to the Rayleigh quotient of the normalized version of x. And that's going to be a key property that we are going to use going forward. So what we are going to do, because of this, we can actually think of R just as a map from the set of unit vectors to the real numbers. And that's what we're going to use, because the set of unit vectors, also called the unit sphere, is a closed and bounded space, or not space, it's a closed and bounded set of x, if x is finite dimensional, and therefore it's compact. And what that means is that the Rayleigh quotient is going to achieve its minimum and maximum value. Whereas if we take x and we just remove the zero vector, we are not going to get a compact space. We can't necessarily conclude that. The Rayleigh quotient is easiest to compute on eigenvectors. Indeed, if we plug in vi, it spits out lambda I. And let's see why that is. Remember, we can always assume that our input vectors are normalized. So the Rayleigh quotient of vi is just the inner product of vi with hvi, which is the inner product of vi and lambda I vi. We can pull out the real valued lambda, and then vi dot vi is 1, so we just get vi as desired. Let's now give a geometric interpretation as to what this thing really represents. And I'm going to use an example that I've done before. H is 3, 0, 0, 2. A diagonal matrix, but it's not that special because any 2 by 2 self-adjoint matrix can be thought of as a diagonal matrix if you use your basis of eigenvectors. So I'm going to draw this common picture that I've done before. So we have our standard basis, E1 and E2, and this defines a square grid, our coordinate system. And if we apply H to it, now I might exaggerate a little bit just to emphasize the fact this is a rectangle. I get This is 3e1, and this is 2e2. So that sends this square to a rectangle. And I don't really need much else besides just this. So think about what this is saying. So the Rayleigh quotient at a vector, you take the unit, so if this is v, then you just take v normalized, and then you apply h to that unit vector, and you project that back onto the original normalized vector itself. So what this is saying is what's the scaling factor of h in this direction? So let me explain that. So let's take E1. The Rayleigh quotient of E1 is the inner product of E1 with HE1, which is E1 dot 3 E1, which is 3. And the Rayleigh quotient of E2 is inner product of E2 and HE2, which is E2 dot 2 E2, which is equal to 2. So this thing gets stretched out by a factor of 3. This thing gets stretched out by a factor of 2. So if your inputs are the eigenvectors, the Rayleigh quotient is just telling you how much those get stretched. Let's see what the Rayleigh quotient is for a non-eigenvector. I'm going to start by drawing the unit circle over here. And when we apply h to the unit circle, it maps it to this ellipse. And I don't know how accurately I'm going to draw this, but I'll try. And let's let v be root 2 over 2 e1 plus root 2 over 2 e2. And let's think about what the Rayleigh quotient of v is. Now this is the Rayleigh quotient, if you prefer, of 1, 1, because it ignores scalars. So h sends this vector, so it sends this entire line to this entire line right here. So this right here is going to be HV. And the geometric meaning of this is we take the unit vector, we apply h to it, and then we project it onto the original direction. So in other words, the original direction is this 45-degree angle. I don't know how well I'm drawing this. And so we are measuring this length. So we're applying h, and we're projecting that onto the original direction. Notice that is exactly what's happening with the eigenvectors. So we scale E1 and project it onto that line, and we get 3. We scale E2 by 2 and project it onto that original line, we get 2. And that's what we're doing here. We just project it onto a different line because it's not an eigenvector. So it makes sense that HV, or I should say the Rayleigh quotient of V, is going to be between 2 and 3. Because this scaling factor is going to be strictly less than 3, but also strictly bigger than 2. And let's check that. So in general, if V equals A1 E1 plus A2 E2, then the Rayleigh quotient of V is just going to be lambda 1 A1 squared plus lambda 2 A2 squared. In this case, that's going to be 3 A1 squared plus 2 A2 squared. Well, in this case, A1 and A2 are root 2 over 2. And so that's the square of that, each of those is 1/2. So in this case, it's going to be 3 times 1/2 plus 2 times 1/2, and that's going to be 2.5. So indeed, the Rayleigh quotient of vector 1, 1, or the normalized version, is going to be 2.5, halfway between E1 and E2. And this is how we can think about the Rayleigh quotient in general of a non-unit vector. So if we have a vector x, which is A1, E1 plus A2 E2 all the way up to AN EN. Well, we can assume it's a unit vector, which means that A1 squared plus A2 squared, that the sum of the squares of the coefficients are equal to 1. And so the Rayleigh quotient of x is going to be lambda 1 A1 squared plus lambda 2 A2 squared plus lambda n AN squared. And so if you think about an arbitrary vector, you can ask what are the dominant directions. So the coefficients square up to 1. So, so some of these might be 0 or close to 0. Some of these might be 0.5, 0.6 large fractions. Those are going to contribute more. So the Rayleigh quotient is taking a linear combination of the squares of the coefficients weighted by the eigenvectors. Intuitively, it seems like if you do this, you can't ever get larger than the maximum eigenvalue lambda n. Now, how can you ever get the largest eigenvector? Well, you need everything here to be 0 for that to happen. So the largest this thing can be is lambda n, and similarly, the smallest this could be is lambda 1. So that's going to happen if A1 equals 1, and then all of the other AIs are going to be 0. So in other words, the Rayleigh quotient is maximized at the largest eigenvector. So with respect to our eigenvector basis, that's 0, 0, 1. So this is Vn. And it's going to be minimized at the smallest, or the eigen. So I'm going to, throughout this lecture and the next, I'm going to speak about the largest eigenvector and the smallest eigenvector to be shorthand for the eigenvector of the largest eigenvalue and the eigenvector of the smallest eigenvalue. It's just easier to say it that way. So it's going to be minimized here and maximized here. Now I haven't proven that, but it seems very intuitive when you think about it this way. And so we will definitely establish this in the remaining part of this lecture, and we will analyze it a little more analytically. Formally, I will show that not only the maximum and minimum values, but all of the critical points from a calculus perspective occur at the eigenvectors of H. And from that, we will deduce that H must have a full set of eigenvectors. Even though we know this is the case, that result comes from spectral theory of linear maps. So we will actually prove that directly in this lecture without going that route. Let me reiterate something I said earlier, that since the Rayleigh quotient ignores the scaling factor of x, we can think of R as being a map from the unit sphere. Since x is finite dimensional, the unit sphere is compact. If you haven't taken real analysis and haven't seen this word, don't worry about it. Just think that it's closed and bounded, and it's a fundamental property of continuous functions, of which the Rayleigh quotient is. Not going to prove that, but it's at least believable, that they achieve their minimum and maximum values on a compact set. What do I mean by achieve their minimum and maximum values? Again, this is a real analysis detail that I don't really need to worry about too much, but not all functions achieve their max and minimum values. Like f of x equals e to the x does not achieve its minimum value on the real line. It gets closer and closer to 0, never actually gets there. So we can't talk about the minimum of e to the x. We can only talk about the greatest lower bound of e to the x, which is 0. But e to the x is never 0. Basically, we don't have to worry about that for the Rayleigh quotient because of compactness. In other words, there is a vector v min and a vector v max where the Rayleigh quotient actually achieves its minimum and maximum value. And I've already explained really what these are. So those minimum and maximum values are the minimum and maximum eigenvalues, and these vectors are the corresponding eigenvectors. Though I have hopefully convinced you intuitively, I haven't actually proven why the Rayleigh quotient is minimized at an eigenvector. So let's let v be a unit vector that minimizes the Rayleigh quotient. And let's say that the minimum value is equal to lambda. I'm going to prove to you why v and lambda are eigenvector-eigenvalue pairs. And moreover, why lambda is indeed the smallest eigenvalue of h. And we will do this by taking any other vector w, a parameter t, and considering the real valued function of t, r of v plus tw. Now what are we really doing here? This is v. This is some vector in a large n-dimensional vector space. And since the Rayleigh quotient is minimized here, that means if we go in any other direction, it's either staying the same or getting bigger. So let's pick another direction. Let's call this w. And then v plus tw is parametrizing the path through p in that direction. And because it achieves a minimum here, then this is a critical point, a local minimum of this single variable function. So think in the calculus sense. So what I will do is write r of v plus tw. I'm going to simplify it a little bit and then take the derivative and set it equal to 0. And I claim that if we do that, we will get that h v equals lambda v. This is what we're trying to figure out. Actually, I didn't need to write that down. I had it right here. Okay, so r of v plus tw, by definition, is v plus tw, h of v plus tw, divided by v plus tw, v plus tw. Now I'm just going to use bilinearity and break this apart. So this is v hv plus, let's see, we're going to have two terms that have a t in it. So we're going to have a t w hv plus v hw. Hope you can handle that. Plus, now there's going to be a t squared. There's going to be a t squared times w hw. Okay, that's the top. And now the bottom is going to be a little bit easier. It's v dot v plus, there's going to be two terms with a t in it. T times w dot v plus v dot w plus t squared times w dot w. Okay, so let me call this thing on the, so to take the derivative, I'm going to have to apply the quotient rule. So what do I want to call this? Have I used f and g? Let me call this f of t and g of t. Okay, so now the derivative of r of v plus tw. Wait, so we have to set the derivative and or take the derivative and set it equal to 0. So it's going to be f prime. Well, actually, what I'm going to do is I'm going to do this at t equals 0. So it's going to be f prime of 0 times g of 0 minus f of 0 g prime of 0 over g of 0 squared. Okay, and we're going to set this equal to 0, so I don't really care too much about what the bottom is. Because for this to be 0, the top has to be 0. So, okay, so what is this? Let's actually compute these. So let's compute f of 0, g of 0, and so forth. So I'm going to use a different color and also go up here. So let's start with f of 0. So you can get that by plugging 0 in for t. This goes away, and you are left with v dot hv. This is also the Rayleigh quotient of v. You could have also gotten that by just plugging in 0 for w, or for t right here, and you get rv. So this is the Rayleigh quotient of v, and this is lambda. I mean, that's, we're assuming, that's by definition of v and lambda. Next, let's compute f prime of 0. So the derivative of this is a polynomial, a degree 2 polynomial in t. If you take the derivative, the constant term goes away. The quadratic term turns into a t. Plugging in 0 makes that go away. And so we're just left with the coefficient of the linear term. And so this is inner product of w with hv plus the inner product of v with hw. I can move the h over to the left-hand side. Let me just do that. So hv dot w. And now this thing here, notice that if I want to combine these things, I can swap the order of these coordinates, but I have to put a complex conjugate on top of that. And now, so if you take z bar plus z, you get 2 times the real part of z. We've been over that. So this is going to be 2 times the real part of hvw. So that's f of 0. Next, g of 0. That's what you get when you plug 0 into the bottom of this. Again, the t squared and the t goes away. You're left with v dot v. Since v is a unit vector, that's equal to 1. And now g prime of 0. Once again, this is a degree 2 polynomial. Take the derivative, plug in 0. You just get the coefficient of t. And so we can combine these as before. And we get 2 times the real part of v dot w. Okay, so now we are ready to plug this back into here. And let's see how to do that. So this first term is going to be 2 times the real part times 1. So in other words, we get 2 times the real part of hv and w dot w times 1 minus f of 0, so that's lambda, times 2 times the real part of v dot w. So lambda times 2 real part of v dot w. And then over g of 0 squared, I don't really care about. I'm just going to leave it as g of 0 squared because we're setting this thing equal to 0. So we don't care about the denominator, just the numerator. Okay, so now what can we do here? So I can factor out a 2. I can combine these two using bilinearity. If we do that, we get a 2 times, let's see, so I'm going to move the lambda inside and put it next to the v. So 2 times the real part of hv minus lambda v dot w over g of 0 squared. So again, I moved the lambda in here, then I combined these using bilinearity, and this is equal to 0. So now this holds for all w in x. So I don't care what vector I pick for w, we have this. And so in other words, if the real part of this complex number is 0 for all w, then that first argument has to be equal to 0. So that tells us that hv minus lambda v equals 0. And that's exactly what we wanted to show, that lambda and v are an eigenvalue eigenvector pair. Moreover, it is clear that lambda is indeed the smallest eigenvalue of H. We just showed that the minimum value of the Rayleigh quotient is the smallest eigenvalue, and this is achieved at the corresponding eigenvector. This eigenvector spans a one-dimensional subspace, so its orthogonal complement, which we will call x1, is n-1 dimensional, and the vector space X is the direct sum of x1 and the span of v1, which are orthogonal complements. Our next goal is to basically iterate our previous process on x1 and pick off the smallest eigenvalue of H restricted to that space, which will be the second smallest eigenvalue of H, and then repeat. So if v2 is the corresponding eigenvector, then v1 and v2 span a two-dimensional subspace, and the orthogonal complement is n-2 dimensions. So we can restrict H to that space and get the third smallest eigenvalue, and so forth. Now, to do this, what we need is for x1 to be H invariant. So here's a picture of what we have. So we have v1 spans a one-dimensional subspace, and then x1 is characterized by being the set of vectors that are orthogonal to v1. So we have to show that if we take anything, let's say x, that's orthogonal to v1, and we apply h, it remains orthogonal to v1. In other words, for part 1, we need to show that if v1 dot x is equal to 0, then v1 dot hx better be 0 as well. And indeed, we can write this as hv1 x, which is lambda 1 v1 x. We can pull out the lambda 1 and get v1 dot x, and this is equal to 0 by our assumption. So that confirms part 1. Now I'm going to write out a few more things for 2 and 3. I've basically said it all. So let v2 be the vector in x1, be, I'm going to say, a unit vector. There may be more than one. There may be repeated eigenvalue. We can also, multiply by -1. Doesn't change anything. Be a unit vector that minimizes the Rayleigh quotient of x. In other words, R of v2 is the minimum of R of x, where x is in x1. I don't need to actually say that it's a unit vector. We just have to assume it's non-zero. And let's say that that is minimized at lambda 2. Then we know that h times v2 equals lambda 2 v2. And so this must be the second smallest eigenvalue. And so we repeat this process. Again, we define x2 to be the span of v1 and v2. And then we let v3 be the element of v2, be the one that minimizes R of x on x2. And we repeat this process, and we get that R of v3 is some value, let's call it lambda 3. And what we get overall is we get lambda 1 is less than or equal to lambda 2. We are literally constructing the eigenvalues and corresponding eigenvectors in increasing order. So this is a way to construct the spectral resolution of a self-adjoint map without appealing to the spectral theory of linear maps and things like the fundamental theorem of algebra. Now that we have constructed the eigenvalues of a self-adjoint linear map, we can characterize them with with something that's called the min-max principle. And formally, it says that the kth smallest eigenvalue, lambda k, is the minimum taken over all k-dimensional subspaces of the maximum of the Rayleigh quotient. So this is one of those things that no matter how many times you see it, or at least for me anyways, I still always have to wrap my head around it. And you'll see things like this, minimum of maximum of a quantity, or the maximum of a minimum of a quantity in a lot of areas of math, especially like analysis and optimization. So I think the best way to motivate what this is really saying is to do an example. So I will let h be, I'm going to extend our example of 3, 2, let's say 3, 2, 4. So this is a 3 by 3 matrix. And now my picture is going to look like this. So I have my standard unit cube. Say this is E1, this is E2, and this is E3. Oops, E3. And you apply h to it. And again, I might exaggerate the stretching if needed. So E1 gets stretched by a factor of 3. This is 3E1. E2 gets stretched by a factor of 2, 2E2. And then E3 gets stretched by a factor of 4. So this is, say, 4E3. And now let me draw that, be careful, and draw that rectangular box. So this is the image of the unit cube. It's easy to see that the eigenvalues in increasing order are 2, 3, and 4. So what does this min-max principle tell us about that? So first of all, the smallest eigenvalue, lambda 1, so we take all one-dimensional subspaces, so all lines through the origin, and we take the maximum, well, the Rayleigh quotient is constant over any line. So lambda 1 is the smallest that the Rayleigh quotient can be. And sure, that's 2. We take this subspace, the y-axis. Next, I'm going to skip over to lambda 3. Lambda 3, the third smallest eigenvalue, we take all 3-dimensional subspaces. There's only one of them, the whole thing, and we maximize the Rayleigh quotient on that. So that's 4. There's nothing interesting there either. So really, the only interesting part here is this middle one, the second largest eigenvalue. So what is this saying? It's saying let's take all 2-dimensional subspaces. So picture every possible plane through the origin. You have the xy axis, you got the yz axis, and the xz axis. So you got 3 coordinate, planes. You got 3 coordinate planes, but you also have a lot of them that, infinitely many of them, that tilt sort of in a diagonal or in a crooked fashion. You got to take all of those into account as well. And so this is saying, how do you minimize the largest that the Rayleigh quotient is going to be? And just for reference, let's consider these 3 coordinate planes. So let's take the xy plane. So the Rayleigh quotient, so the max of the Rayleigh quotient on the xy plane is going to be 3, right? Because this is something that we've done before. This is eigenvalues 3, this one's 2. Let's take the yz plane. So the xy plane is that one. The yz plane is going to be that one. So here, the maximum that the Rayleigh quotient is going to be 4, because you got an eigenvalue of 2 and one of 4. So the maximum of the Rayleigh quotient is equal to 4. And then finally, the xz plane, that's going to be this one, like here, the xz plane. So here's the x-axis, here's the z-axis. And now the Rayleigh quotient is going to take a value of 4 along the z-axis. So the maximum of the Rayleigh quotient is 4. So this is saying what's the minimum that the maximum is going to be. So just looking at these three, it's clear that this is the winner. So I like to think of this as saying, how low can you push down the maximum value of the Rayleigh quotient? Here it's going to be 4. Here it's 4. Here you can push it all the way down to 3. And what this is saying is that you can't push it down any further. The second smallest eigenvalue is as far as you can push down the maximum value. And loosely speaking, that's because you can take the subspace spanned by V1 and V2, or just in general, spanned by V1 up to Vk, and that is going to be a k-dimensional subspace. And the Rayleigh quotient is, the maximum Rayleigh quotient is lambda k. And you can't ever get the Rayleigh quotient, the maximum value, below that. You can get it above that, as you can see here, but you can't push it below 3. And you can try to say, well, what about a plane that sort of goes off in, I don't know how to draw this, in some crooked direction like this. This vector x is going to have some component. Think about what x, say it's a unit vector. X is a1 e1 plus a2 e2 plus a3 e3. It's going to have some component in this vertical direction, and that's going to ruin any chance of getting it below 3 here. So again, if these eigenvectors are, well, I guess I didn't order them. Unfortunately, I guess this is my V1, this is my V2, and this is my V3 here, a little bit out of order. But the point is, as long as you have any bit of an E3 in here, there's no way that the maximum Rayleigh quotient is going to be minimized. Okay, so that's kind of the intuition. This is really the only Goldilocks example that I have, because if you got a 4-dimensional subspace, you can't visualize it. And for a 3-dimensional space, as I've said, the smallest and the largest eigenvalues are not that interesting. So to prove this, there's basically 2 things you got to do. And you could formally write it down and formalize it as show that you have a less than and greater than or equal to both hold. But I think it's easier just to it's equivalent to this, do 2 things. First of all, show that there is a subspace where, show that there is a k-dimensional subspace where the maximum value is lambda k. That's namely this thing right here. And then show that for any k-dimensional subspace, the maximum value is at least lambda k. So one of those things will show less than or equal to, the other one will show greater than or equal to. So note, if we let t be equal to the span, actually I'm going to call this S. S be equal to the span of V1 up to Vk, then, so we are picking this particular subspace, and we're saying then the maximum Rayleigh quotient, we've already done this, the maximum of the Rayleigh quotient of x for x and s is equal to lambda k. This is the largest eigenvalue. Okay, so for the other direction, let's take an arbitrary k-dimensional space. Let's show that the maximum has to be at least this. So what this has done is saying that the maximum value the minimum of the maximum has to be less than or equal to lambda k. Because here's one where the maximum is lambda k. Maybe there's another one where the maximum is less than this. We can't rule that out. What we basically did is we just showed that direction. Let's show the other one. Let's take an arbitrary k-dimensional subspace. So let dimension of S be equal to k. We don't have any choice as to what that is. Now I will let T be the span of Vk all the way up to Vn. And what I claim is that S and T intersect non-trivially. And that's a problem because, well, not a problem, that helps us solve this. If they intersect non-trivially, then we take any vector, and the Rayleigh quotient of that vector is going to be at least lambda k, because it only is made up of these larger eigenvectors. So how do we do that? Well, the dimension, let's take s plus t. The dimension of this has to be less than or equal to n, because n is the dimension of the space. So this is the dimension of x. But we also know that the dimension of s plus t from the very first section of lectures is the dimension of s plus the dimension of t minus the dimension of their intersection. So the dimension of s, I've already said, is k. The dimension of t, well, x is n-dimensional, and here we are removing k minus 1 vectors, so that's n. The dimension is n minus k minus 1, which is n minus k plus 1. So this is n minus k plus 1 minus the dimension, let's call this d. This is less than or equal to n. So the k's will cancel. And now we have n plus 1 minus d is less than or equal to n. And we get immediately that d has to be at least 1. So now we can take any x in s intersect t. We can assume it's a unit vector. And x then is equal to ak vk plus all the way up to an vn. And we know that ak squared dot dot plus dot 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 an squared, the sum of these coefficients is 1. So we can eliminate the first k minus 1 basis vectors because t is spanned by vk up to vn. So now the Rayleigh quotient of x is the sum of j equals k up to n of lambda j times a j squared, and what we can do now is, because we have this ordering of the eigenvalues, we can replace all of these eigenvalues with the smallest one, which is lambda k. That's the smallest of the eigenvalues from k up to n. And so let's do that. J equals k up to n. If we replace this with lambda k a j squared. Now what have we done? We have made this less than or equal to the original sum. So now we can just pull out the lambda k, right? J equals k to n of a j squared, and this is equal to 1. So this is equal to lambda k. So that completes the proof. We have taken an arbitrary k-dimensional subspace, and we have shown that it has a vector whose Rayleigh quotient is at least mk, lambda k. In other words, we can't push down that maximum value below lambda k. We've already shown that there is one that achieves that as its maximum value. So that proves this inequality and the theorem. Finally, it's worth noting that what we did was characterize the kth largest eigenvalue as the minimum of the maximum of the Rayleigh quotient. And there is an analogous characterization of the kth smallest eigenvalue, where we count down as the maximum of the minimum of the Rayleigh quotient. And I will let you think about how to formulate and prove that yourself. It's a good exercise. I think I'll put that on the homework. Let's conclude this lecture with a quick summary and a word about applications of the Rayleigh quotient. So for a self-adjoint map H, the Rayleigh quotient is defined on all non-zero vectors, And it's the inner product of x with hx divided by the inner product of x squared, which I like to think of this as taking, so if you have your vector x, you normalize it, you take the one, you scale it down so it's on it, or up so it's on the unit cube, and then you apply h to that vector. So this is the normalized version of x, this is h times the normalized version of x, and you project that image onto the original direction, and that length is the Rayleigh quotient. The eigenvectors of h are the critical points of the Rayleigh quotient. That is, the first derivatives are 0 if and only if we are at an eigenvector. And a full proof of this has to go into multivariable calculus and a discussion about derivatives, and I'm not going to do that. So I think this is just an important takeaway point that if you wanted to, you could spend more time going into detail and understanding this better. At any eigenvector, vi, the Rayleigh quotient evaluates at lambda I, the corresponding eigenvalue. In particular, the minimum of the Rayleigh quotient is the smallest eigenvalue, and the maximum is the largest eigenvalue. Finally, a quick word about applications of the Rayleigh quotient. So this comes up in numerical linear algebra in algorithms that estimate an eigenvalue and eigenvector of a linear map. So in particular, suppose we have a real symmetric matrix H, and we want to find an eigenvalue and eigenvector. So if we are in the neighborhood of that eigenvector, in other words, if we are within epsilon, so here's a picture of that. So suppose we have this V. If we are within an epsilon ball, so this has radius epsilon. So if W is any other vector in this ball, then if we compute the Rayleigh quotient of W, that will give us, that will be within a factor of epsilon squared of lambda. So in other words, this is a second order approximation of the actual eigenvalue. And so what you can do is you can guess an eigenvector and use that to get a better estimation of an eigenvalue, and then use that to get a better estimation of the eigenvector, and just iterate this until you get closer and closer, and it converges pretty quickly. So in other words, the Rayleigh quotient is a second order Taylor approximation of the eigenvalue. So that's the tip of the iceberg. I'll let you Google that if you want to learn more. Coming up next, we will introduce the so-called generalized Rayleigh quotient, which really is just the Rayleigh quotient, but with respect to a different inner product. So stay with us.